dele. Bom, eu acho que eu não preciso disso. Bom, it's a pleasure and an honor to introduce our friend, good English friend, very Lawson, who will talk on cycles and Spectra.
So, thank you very much, Manfredo. I'm sorry to interrupt the game. I don't think this will be as interesting.
Argentina is gone now.
Yeah. So I'm particularly honored by all of you who watched the game last night and came this morning. So anyway, it is also a pleasure and an honor for me to be invited to speak here at this occasion. IMPA was very important in my own mathematical life. I came here when I was just 2 years from my PhD, and the atmosphere was so wonderful. I think I did some of the best work of my life while I was here. I met some truly remarkable people. It's a small group of dedicated and enormously talented people who created IMPA and turned it into a central institution in mathematics in the world. It really has played, obviously, a huge role in South American mathematics, but clearly also a huge role in mathematics worldwide. So I'm proud to be here. It's wonderful. So today, I want to talk about a topic that is somewhere between topology and algebraic geometry. How do I turn this on? Is there a... In the front? Oh, that's the front. Okay. Okay, and the work that I'm going to talk about has been done largely in conjunction with 3 other mathematicians. And if you notice, Pedro, Paulo, and Maria. I've been trying to get them to sing together, but we haven't done it yet. Anyway, there's a theme to what I want to say, and that is that spaces of algebraic cycles form natural models for classifying spaces in topology. This is the general theme of what I want to say. And the point is that, this fact tells us a lot about spaces of cycles, and it also goes the other way. We knew this in some fundamental way years ago, but there have been some recent results that show that this is in fact a much more profound phenomenon than we thought, and that's basically what I want to talk about today. So it's always good to begin with an example, and so actually I'll begin with a theorem. It's always nice to begin with a theorem that everyone can understand before everyone gets hopelessly bored. So the first example comes from symmetric products. So the symmetric product of a space is a very simple construction. You start with a topological space. You take its d-fold Cartesian product, and then you divide by the symmetric group acting by permutations of the factors. Okay, so this is obviously, again, a topological space in the quotient topology. And I want to look at this in a particular case. I want to look at complex projective space. So I remind you the complex projective n space is just the space of all, it's the set of all one-dimensional linear subspaces in a vector space of dimension n plus 1, which we might as well take to be Cn plus 1. And this is the quotient of all the non-zero vectors in Cn plus 1 by the action of the scalars. And obviously, every non-zero vector determines a one-dimensional subspace. Two such vectors determine the same one if and only if they differ by scalar multiplication. And I remind you that the one-dimensional projective space is just the Riemann sphere, the one-point compactification of the real line. So now the theorem is a statement that the d-fold symmetric product of projective 1 space, complex projective 1 space, is complex projective D space. Now, if you think a little bit about this, it's rather surprising. I mean, even if you start with x the circle, when you start taking symmetric products, you get folds and singularities of all sorts. And that's, in fact, the general phenomenon. It's really only in the case of surfaces that you get something quite so nice. So this is really a rather beautiful and unexpected result. And it'd be nice to see how you, as long as we have it put up here, we might as well prove it. So what's the proof? Well, so let me remind you about homogeneous coordinates. So projective space is just this quotient of Cn plus 1. So points in Cn plus 1 are called homogeneous coordinates for the space. They're not coordinates in the usual sense. They're redundant. But nevertheless, let's think this way. So if I'm given d points in the projective line, I'm going to choose homogeneous coordinates in this rather strange way. The first coordinate is minus bi, and the second is ai. Actually, is there a pointer? Ah, okay. I'm not going to know how to use this either. Oh. There we go. Okay. So it's minus bi and ai. And then given this, I form the homogeneous polynomial, as you see, aix plus biy, which obviously has roots given by these pi's. This is a homogeneous polynomial of degree d, so I expand out and I get coefficients, and these coefficients simply are written like this. And notice that it's a sum over multi-indices. The kth coefficient is over multi-indices of length k, where the b's appear with the complementary indices. So in each of these, you get either one ai or bi for each I appears. And so this gives us a well-defined map. It's easy to see that this gives us a well-defined map from symmetric product into projective space by just associating to the polynomials, to these points, these particular polynomials in the homogeneous coordinates. That's a well-defined map. Okay. And that well-defined map has an inverse, which simply assigns to a polynomial its roots. Okay, the homogeneous polynomial has roots, which are again points in P1. Okay, so it's easy to check it's a bijection, and it's algebraic, so it's certainly smooth. Now, there's a little bit more that you can notice about this. The first has to do with algebraic structure. So another way of writing the default symmetric product is to think of the points in there as formal sums with integer coefficients of the points in the space. But here I'm assuming that the points in X are distinct. So you take d points, some of them are the same, you put them together, and simply give them a positive integer coefficient. If you think of it that way, then it's clear that the disjoint union of these spaces has a group structure, right? Just addition. And that group structure is also obviously continuous. So this disjoint union becomes an abelian topological monoid. Okay? And now there's another bit of structure that comes with this, and that's a real structure. Whenever you have a space with an involution, in fact, with any continuous map, the continuous map extends to the default symmetric product, and if it's an involution, if the square is the identity, then the induced map on the symmetric product is the identity. Now, there are two, an involution is called a real structure. This is Atiyah's sense of a real structure. But, Atiyah's real structures arose in a natural way from algebraic geometry. If you have a variety defined over the real numbers, and you look at the complex points, then the Galois group of the complex numbers over the reals, which is just Z mod 2, acts on the complex points, okay, as an involution, and it acts continuously on the complex points. So, so it turns out that complex projective space has two real structures. So the first is the standard real structure. Well, if you think of homogeneous coordinates as Cn, then just take complex conjugation in homogeneous coordinates, and that's a map it's real linear, but it also sends a line, a one-dimensional complex space, to a one-dimensional complex space, albeit anti-linearly. Okay? And it induces So the standard complex conjugation gives you an involutional projective space whose fixed point set is just the real projective space, the real variety. And so it induces an involution on the d-fold symmetric product, which we know to be projective space from that theorem. And that involution is, again, the real involution. So if you take the real involution on P1, and then take the induced one on the d-fold symmetric product, that's the standard real involution on PD. But there's a second structure, real structure on complex projective space. This is the so-called Brouwer-Savary structure. And for this, we have to pass to the quaternions. So, somehow as in representation theory, there's a complex representation theory, but the real and quaternionic theories fit naturally with it, right? There are maps between them and so forth, and we're going to see a lot of that today. So what's the other structure? You consider, let's look at quaternionic projective space of dimension D. That's a complex space of dimension 2D. So if you forget about the quaternionic structure, this is a complex vector space, and you can take its complex projective space. Okay, so this is just the complex projective space. It's of dimension 2D minus 1. Then if you remember that it's the quaternions, and you think about left quaternion scalar multiplication by the quaternion J, that's an anti-complex linear map. It anti-commutes with multiplication by I, but it sends one-dimensional subspaces to one-dimensional subspaces. It gives an anti-holomorphic involution of this projective space, okay, whose square is the identity. Well, it's an involution. And it has no fixed points. It has no fixed points. Okay, so it's certainly not equivalent to the original one, which had a very big fixed point set. And if you look at this in the simplest case, just take the two-sphere that you get by looking at the complex projective space of the quaternions themselves. That's called the Brouwer-Savary curve. And so what is it? Well, it's just the two-sphere with a fixed point-free and anti-holomorphic involution. So what could it be but the antipodal map? And that's what it is. Okay. And I think in the general situation, if you want the geometric picture, the complex projective space of odd dimension fibers over the quaternionic projective space, and the fibers are all projective lines. And this involution is just the antipodal map on those lines. That's what it does. So now we start with this other involution on P1, thinking of it as the Brouwer-Savary curve, and we take the d-fold symmetric product, and we get then involutions, real structures on the associated projective spaces. And what do you get? Well, in the case that D is odd, it turns out that this is exactly the Brouwer-Savary involution, the quaternionic involution. But when D is even, there's no hope that it can be that, because this only takes place on the odd dimensional ones. And so it's the standard one. And this is very easy to check using the coordinates that I wrote down before, the A's, the B's, and the C's. You can just see directly in an elementary way that that's true. Okay, so we're going to see this pattern when we come to algebraic cycles. Now, let me talk a little bit about group completion. So remember, the symmetric product, which was the disjoint union of all these d-fold symmetric products, was in a topological abelian monoid. And so you can take its group completion, just the usual way you make the integers out of the positive integers. Take the product of the monoid with itself and divide by the obvious relation, which is closed. This turns this thing into a topological abelian group, which is nothing more than the free abelian group on the space. Take the points of the space and do this stupid thing. Take the free abelian group on it. That's not interesting in general, but in this case, it carries a very pretty topology, a compactly generated topology. Okay, so it's in fact a topological space, which is an abelian group. And there's a question of what this looks like. So one way to understand this is the following. If you fix a base point in this space, then there's a natural sort of sequence of embeddings of the symmetric products one into the next, which is gotten by just sending an element in the space to what you get by adding on the base point. So you just, by adding on the base point, you get a sequence of embeddings. And the limit with the limit topology is called the infinite symmetric product, and it's a classical theorem of Dold-Thom that the connected component in this abelian group, here I should assume that X is connected. So if X is connected and reasonably nice, like a finite complex, then the connected component in this abelian group is homotopy equivalent to the infinite symmetric product. So the infinite symmetric product is something you can understand because it's the limit sort of finite dimensional spaces, something you can really compute. Okay, so this abelian group is essentially the same thing as the symmetric product, and understanding symmetric products goes back to Steenrod, the infancy of topology practically. Okay, so this brings us to algebraic cycles. So what are algebraic cycles? So a subset of projective space is an algebraic variety if in homogeneous coordinates it's defined by a finite number of homogeneous polynomial equations. Right? That's what an algebraic variety is. And such a thing is irreducible if it can't be written in a non-trivial way as a union of two such varieties. And that turns out to be equivalent to the fact that the manifold points, the so-called regular set of this, the set of points in which in a neighborhood it's really a submanifold, is a connected set. If it's connected, then it has a dimension. Right? The manifold points are connected. There's a unique dimension. That's called the dimension of the variety. Now, one of the principal points of one of the principal insights at the really elementary level that Grothendieck had was that if you want to extend the theory, sort of classical theory of algebraic varieties defined over a field to more general, to quote varieties defined over some more general ring, then you have to consider the points of the variety not just to be the usual classical points, but you have to consider all the irreducible subvarieties of all dimensions. Okay? And so even in the affine case, instead of just considering the maximum, in the case of an affine algebraic variety, instead of just considering the maximal ideals, which are the points, you consider all the subvarieties, and that's called the spectrum of the ring. It corresponds to all the prime ideals in the ring of functions. So if the points of the space are going to be the irreducible algebraic subvarieties, we might as well collect them according to dimensions. So for each dimension p, you can look at the p-dimensional points of the space. And now let's go back. We were thinking about the symmetric product. That was just a free abelian monoid generated by the points of the space. So we can take the free abelian monoid generated by the p-dimensional points of the space. And those are the so-called effective algebraic cycles of dimension p, things which are a finite sum with positive integer coefficients of irreducible p-dimensional subvarieties. Now, it's a theorem of Chow that this breaks into a disjoint union of subsets, each of which has the structure of a projective algebraic variety. So this is now a non-trivial theorem, but it's comprehensible. It's a hands-on geometric construction. And so this is, again, a union of compact Hausdorff spaces. Okay? And it obviously has an addition on it, which is continuous. And so one can, again, group complete it, and you get a topological group, a topological abelian group. That's supposed to be a V. I was asleep. So anyway, that X is supposed to be a V. Topological abelian group generated by the irreducible subvarieties, and this is called the group of algebraic P cycles. Okay? And now, the first theorem that in the latter part of the century I wanted to mention was the total analog of the theory of the theorem of Dold-Thom, which was proved by Paulo Lima Filho back in 1993, and was also proved independently by Friedlander and Gabor. But so Paulo was competing with some pretty heavy hitters, and he proved it first actually. But he proved that if, again, it's the same sort of thing. There is a natural limit, which looks like this limit of symmetric products, which is gotten by, well, it's a natural limit over the connected components here by translations. And that homotopy limit is homotopy equivalent to the group, the free abelian group. So again, this means that the content of this is that the homotopy groups of this group are the same as the direct limit of the homotopy groups of these pieces and the homology groups and so forth. So back here on these things which are very interesting geometric objects, when you stabilize, you get exactly the homotopy invariance of this group. Okay. Now this brings me to, there's one theorem in this subject which is not, well, there is a theorem in this subject which is not so completely obvious. It has to do with something that I call algebraic suspension. So suppose we start with a subvariety of projective n space and embed n space into projective n plus 1 space as a hyperplane, just a linear hyperplane. Take a point that's not in that hyperplane, then to every subvariety in Pn, you can associate the so-called algebraic suspension of this, or sometimes called the cone, which is just the union of all lines joining x to this point. This is again an algebraic variety. It's defined it's defined by the same polynomials in homogeneous coordinates that define x, but now these polynomials are polynomials in one additional variable. So upstairs you take your original cone and you cross it with a complex line and then you reproject it. Okay. So the theorem is that this map is obviously a very natural map. It's going to take subvarieties of irreducible subvarieties of x to irreducible subvarieties, and you extend linearly, and it gives you a continuous homomorphism from the p cycles on x to the p plus 1 cycles on the suspension. And the theorem is that this is a homotopy equivalence of spaces. So for example, it has the corollary that the p cycles on projective n space are the same as the p plus 1 cycles up to homotopy on projective n plus 1 space and so forth, because the suspension of projective space is just the projective space of one higher dimension. So let me give you a really quick idea of the proof of this. So the first thing to do is to observe that that this is when you take a projective space and then a point in a linear hyperplane and a point, if you remove this point, what's left over is a vector bundle, complex line bundle, right? O of 1. And in particular, you have scalar multiplication by complex numbers in that line bundle, and you have scalar multiplication in particular by positive real numbers. So that scalar multiplication by positive real numbers is a flow on projective space. It fixes this hyperplane, and it fixes this point, and everything else, is attracted to this point. It's a very simple flow. And so if you start with a cycle in projective space that meets this hyperplane in general position, what happens to it under the flow is that, of course, the base intersection is fixed, but everything else gets pulled, sort of like taffy. And in the limit, it becomes a suspension cycle. So that shows that all the cycles that meet this hyperplane in proper dimension, that subset is a deformation retract of the suspension cycles, or the other way around. Has a deformation retraction down to the suspension cycles. So you're sort of left with having to prove that the cycles that meet this hyperplane in general position are in some sense topologically dense. In other words, their inclusion is a homotopy equivalence into all cycles. So to do this, what you want to do is to take a cycle that may meet the hyperplane badly and move it. In fact, you have to take whole families of them and move the whole families of cycles so that they meet this hyperplane in general position. So for this, you need a kind of moving lemma. Now, you can't move the cycle, in any given family of cycles so that they all become transversal to something. I mean, that's too much to hope for. But the wonderful thing in algebraic geometry is that if you take those cycles and just multiply them all by some fixed integer d, then you can move them to make every one of them transversal to In fact, you can take two such families, multiply them by d, and then wiggle them so that in all positive time, everything in this family is transversal to everything in that family. Yeah, nice. And here's how you do it. You take Pn, it's sitting as a hyperplane in Pn plus 1, and then you embed that as a hyperplane in Pn plus 2. Okay. Now, I have a cycle which I'm representing by these two red dots. And I pick a point in Pn plus 2. This red cycle is the cycle I'd like to make transversal to Pn. Actually, it looks very transversal at the moment, but you have to imagine it's not. So you suspend it up to a point in Pn plus 2. Now, we're going to fix a divisor, d. This is just the zeros of one homogeneous polynomial of some degree little d. So fix a divisor, this codimension 1 object, in Pn plus 2, and intersect this red cone with the green divisor. Okay, and then you're going to get something that is, you get something which when you project back down sits on top of the thing you started with, but it's getting multiplied by d, where d is a degree of the divisor. Here it looks like 3. So you go up, you intersect, and you push down, and you get 3 times what you started with. So what we want to do is not to project down from the same point, but we choose a nearby point and project down from that. And when you do that, these 6 points get pushed down to 6 points in the base, which are slightly displaced from where they started. And now if you move that blue point upstairs closer and closer to the red point, these 6 points will eventually coalesce and become 3 times the thing you started with. That's the movement that works. If you make d big enough, you can show that there are lots and lots of divisors that will move. You start with a family of cycles, and then there's a divisor, in fact, the generic divisor of sufficiently high degree. When you apply this process, using it will move cycles into general position. Okay. Okay, so now let me change topics for just a minute and discuss classifying spaces. So what is a classifying space? So I want to start with a functor, something that associates to every topological space, either a set or an abelian group. So it's a functor from the category of spaces to the category of either sets or abelian groups. And to any morphism, that is to any continuous map from x to y, it associates a morphism from phi of x to phi of y. Right? It satisfies some natural conditions. So what's a classifying space for this functor? A classifying space for such a functor, I'm not properly wired, is a topological space, z sub phi, with a property that there's an equivalence of functors between the functor you started with and the functor which is just the homotopy classes of continuous maps from x into this space. So this is, again, a contravariant functor. So you have a continuous map from x to y, then you just pull back the maps. And if z has a group structure, then this will be a group, and so forth and so on. So that's what I mean by a classifying space in this context. And the best thing to do is just look at a whole sequence of examples. So let me do that. So the first example is just the first cohomology of a space. And for the first cohomology of a space with integer coefficients, the classifying space couldn't be simpler. It's just the circle. Okay? And what is the correspondence? Well, the easiest way is to go this way. Suppose you have a map from x into S1, then there's a natural de Rham representative of the first Chern class. I mean, of the generator of the first cohomology group, which is just the normalized arc length. But nevertheless, you take the generator of the first cohomology group, which is just the integers, and you pull it back. Okay? So you just if this is a, yeah. And the same thing is true for the second cohomology group with integer coefficients. Here the space is infinite complex projective space. And again, if you have a continuous map from x into infinite complex projective space, then you essentially pull back the generator in H2, which on finite pieces of this is nothing but the Kähler form, which is again the normalized complex line element, if you like, right? It's a thing which, when you integrate it on a complex curve, gives you its area. Another way of thinking about this is if you have a map from X into S1, which is smooth, if X is a manifold, then you just pull back, take a regular value and pull back, and you get a hypersurface, and that's the Poincare dual of this class. Okay, same thing works here. Okay, so some more examples. Suppose the functor is, if the functor is associates to X the n-dimensional complex vector bundles up to isomorphism. So isomorphism classes of n-dimensional complex vector bundles. So this is just a set now. Then the classifying space is just the stabilized Grassmannian of n-planes in C capital N. So you take a limit over capital N. And so now the Grassmannian, this is just the space of all n-dimensional linear subspaces of Cn, and there's a natural bundle over this, the tautological bundle, whose fiber at a plane P consists of all the vectors in that plane. So it's tautologically the fiber at capital P is capital P. Okay, so you can write it down in this natural way. It's a subset of this product. And now the correspondence is easy. I mean, if you have a map from X into this space, then there is this universal bundle, Cn, sitting over this space. You simply pull it back and you get a bundle over X. And you have to check that if two maps are homotopic, then the bundles that you get are isomorphic. And then you have to construct an inverse to this, which is not that hard. Okay. Other examples, well, suppose, in fact, in order to make, this is, as I said, not a group. The vector bundles of dimension n are not a group. But you can take Whitney's sum of bundles, and that corresponds to taking the disjoint union of these classifying spaces. And then, because this is, again, a topological monoid, you can take its group completion, and that group completion classifies K-theory. Well, that group completion, I'm sorry, is K-theory, and it's classified by maps into the stabilization of this Grassmannian. So let me say this again. If you start with the vector bundles, they don't form a group. However, the disjoint union does form a semigroup. You make a group out of it. That's reduced K-theory. And the associated classifying space is just what you get when you send little n to infinity. Again, you take a natural limit over inclusions. And this space is called BU. Okay, I think I'll skip the last one. So now quickly, what is a spectrum? Well, a spectrum is a sequence of spaces, which I'm now going to think of as classifying spaces. So I suppose I have some big sequence of spaces that are related by the fact that the nth space is homotopy equivalent. In fact, you'd like it to be homeomorphic to the loop space on the successor, loops on Zn plus 1. So this means that Z0 is loops on Z1, it's twofold loops on Z2, and so forth. And this goes on forever. So when this is true, this space Z0 is called an infinite loop space. And the sequence of spaces that you get is called a spectrum. Now, the reason this is important is that when you have such a family of spaces, you think about the functors that they classify. I mean, they automatically give you functors. And it turns out that if these things have a group structure, then this sequence of functors, call it Hn or phi-n, actually satisfy the axioms of the Eilenberg-Steenrod axioms for a cohomology theory. Except for one, and that's the dimension axiom. So generalized cohomology theories sort of correspond to sequences of such classifying spaces. So there's a big industry in algebraic topology in trying to decide when a given space has this infinite loop space structure, because when it does, it automatically gives you a generalized cohomology theory. Okay, so let me give you one example of these, of such a thing. And these are the Eilenberg-MacLane spectra. So let's let phi-n be the functor which associates to X the nth cohomology with coefficients in a group lambda. So fix a finitely generated group lambda. And then the associated classifying space for this exists and is essentially unique up to homotopy type if you stay in the category of countable CW complexes. And it's called an Eilenberg-MacLane space of type lambda n. It's completely characterized up to homotopy type in this category by the fact that it has only one non-trivial homotopy group, and that's lambda in dimension n. All other homotopy groups are 0. So you see the circle is, so you see that the circle is a KZ1. Complex projective, infinite projective space is a KZ2. And KZ mod P1 is simply the infinite sphere divided, so the infinite lens space. Right? You take the odd dimensional sphere and divide by the pth roots of unity and take a limit. And now it's not hard to see that from this homotopy characterization and the fact that the loops on k lambda n plus 1 is homotopy equivalent to k lambda n. So these guys form an omega spectrum, and they classify a theory, and that theory is the whole graded cohomology theory of spaces with coefficients in lambda. So this is sort of the prototypical spectrum. And of course, it wouldn't, if there weren't lots of others, there would be no point in making a big to-do about it. Now, what's the importance of classifying spaces? Well, the first thing is that if you have a classifying space, then for a functor phi, or for a family of functors, then the basic properties of this space can all be, of this functor, can all be figured out geometrically at the universal level. So, for example, if you're thinking about vector bundles, then characteristic classes of vector bundles are completely determined by understanding the cohomology of the classifying space. So this whole wonderful theory of characteristic classes of vector bundles, once you have the classifying space, is nothing more than understanding the cohomology of the Grassmannian. And every cohomology class in the Grassmannian automatically gives you a characteristic class for all vector bundles, which behaves in this natural way. And this is, of course, just the same thing as computing homotopy classes of maps from the Grassmannians into Eilenberg-MacLane spaces, because that classifies cohomology. So another thing is that suppose you're interested in cohomology operations, the cup product in cohomology, or the Steenrod operations. This comes down to simply understanding the cohomology of the classifying spaces, right? Which is, again, just represented by the homotopy classes of maps from Eilenberg-MacLane spaces into themselves. Okay, so everything gets reduced to universal calculations. And this is, of course, very powerful. Once you understand the universal structure of these, then it gets carried over to any space, and then you prove theorems, real theorems in topology and geometry. So there's a second importance of these things, and that is, suppose you can find a good model for classifying spaces, which is where I'm going. Okay, then if it's nice to have these homotopy characterizations of Eilenberg-MacLane spaces, but if you can find a really nice model for one, then it's a lot easier to understand its cohomology, for example. And so if you have such a thing, you can do nice geometric constructions of characteristic classes, and for example, you can prove the de Rham theorem this way by simply proving it once for the Grassmannian, and you're done. And you also get nice representations of Steenrod operations. On the other hand, it goes the other way. Once you know so much about a classifying space, because of its universal properties, and you have a model that you're really interested in, if that model turns out to be a classifying space, you know a lot about it. Okay? So sort of the first really nice example of this was the theorem of Dolden-Tolm, where they showed that the infinite symmetric product of the n-sphere, maybe I should not get too much information here yet. So their theorem is that the infinite symmetric product of the n-sphere is a model for the Eilenberg-MacLane space, KZN. Okay, so this is a very beautiful space. I mean, take the n sphere and look at the infinite symmetric product of this thing. And as you saw, I mean, we saw an example of this was when n was equal to 2, right? And when you take the infinite symmetric product of S2, you get complex CP infinity, P infinity, and that we just saw was the Eilenberg-MacLane space KZ2. They proved a little bit more. They proved that for any connected finite complex Y, the abelian group on Y is homotopy equivalent, as we saw, to Z cross the infinite symmetric product. But this is homotopy equivalent to a product of Eilenberg-MacLane spaces, where in degree n, the group involved is just the nth homology of the space. So what this means is that the homotopy groups of the abelian group on Y are the same thing as the homotopy groups are the same thing as the homology groups with integer coefficients. So this construction, you take a space and you look at the abelian group on it, this construction converts homotopy to homology. It sort of converts the homotopy groups of the homotopy groups of this guy are the homology groups of the space you started with. So all right. So in particular, so what happens if you try to look at the analog of this for algebraic cycles? So let's look at the basic case. I want to use this notation for codimension Q cycles on Pn, because the suspension theorem preserves, complex suspension preserves codimension. So this theorem that I mentioned proves, together with the Dole-Thom theorem, proves that the codimension Q cycles on Pn are naturally, and in fact canonically, a product of Eilenberg-MacLane spaces, KZ2K, you just get things in even dimensions from 0 to dimension Q for any n. Okay, so it's not quite a simple Eilenberg-MacLane space, but it's just a product of them. And so in particular, what we can do is to take a quotient, look at the cycles of in Pn and divide by those which inhabit a fixed hyperplane. Okay, and the quotient I'll think of as the codimension Q cycles on the affine Cn with a certain topology. That is an Eilenberg-MacLane space. So this says that sort of affine algebraic cycles of codimension Q represent the basic Eilenberg-MacLane space, KZ2Q. So here's an example of a model which is quite complicated, right, but is demystified by this homotopy equivalence. Not that this space is so simple, but I mean, you think you know it. Its homotopy groups are certainly simple. So, now there's some relations that are interesting that come out of this, and this sort of typifies what I was saying about how you can get information. So let's go back to the Grassmannians we were discussing. If you look at the Grassmannian of linear subspaces of codimension Q, a linear subspace is certainly a cycle, an algebraic cycle. It's defined by linear equations. And it's a cycle of degree 1. So there's a natural mapping of the Grassmannian of codimension Q linear subspaces into this group of cycles on Pn. And the claim is that, that this very simple inclusion, well, think about it now. This is the Grassmannian, and this is a map into something which is a product of Eilenberg-MacLane spaces. I claim as such, it classifies the total Chern class of the universal bundle. And what that means is that because the universal bundle was the way you classified vector bundles on any space, that the following is true. I mean, if I have a map of X into this Grassmannian, the homotopy classes of such maps are the same thing as dimension Q vector bundles on X, up to isomorphism. And now applying this map, this transforms homotopy classes here to homotopy classes of maps into ZQ, which I now know is homotopy classes of maps into this product of Eilenberg-MacLane spaces, and hence this gives me a transformation from the vector bundles of rank Q to these of degree 1. So it's 1 cross H2 cross H4 dot dot dot. It associates to a vector bundle 1 plus something called C1 of E, dot, 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 up to CQ of E. And this is precisely the total Chern class of the vector bundle by any other modern definition, or you can take that as a definition. There's also an algebraic join. So there's a way of putting a pairing on cycles, and this is something which is really important in the theory. So suppose I have a cycle in Pn, and over in some other completely distinct Pm, I have another cycle W. Then I can put the two of them, Pn and Pm, disjointly in a Pn plus m plus 1. This m should be n prime. Sorry. And then these disjoint cycles can go together to form a cycle of codimension q plus q prime by simply taking the union of all the lines joining V to W. So it's like the usual join. You just take all the lines joining this one to that one. And that union is, again, an algebraic variety. The polynomials that define it are just simply the same polynomials defining V and W taken together. And the theorem that Marie-Louise and I proved was that this gives a natural mapping from codimension q cycles cross codimension q prime cycles to codimension q plus q prime cycles. The ends don't matter. And that mapping classifies the cup product. That is the map that classifies the cup product. So in particular, if you put this together with a former theorem, you get this standard Whitney duality that the total Chern class of the direct sum of two bundles is the product of the total Chern classes. Yeah. So now a little bit more is true. So where am I? Wait, 48. Well, I'll try to say this quickly. In fact, this is a theorem that was proved by a whole team of people, including Powell. It turns out that there's actually, on this, when you stabilize the cycles, the algebraic cycles, by letting the codimension go to infinity, then this join construction actually gives a pairing. So this is the algebraic join, giving a pairing on the codimension on all these cycles. And there's a natural map from the corresponding stabilization of the Grassmannians, which, as I said, classifies K-theory. And so you get a map from the classifying space for K-theory into this classifying space for even cohomology. This classifies even cohomology. And this map is just the total Chern class map from K-theory to even cohomology. But now, the theorem is that there's actually an infinite loop space structure on this guy that makes this map an infinite loop map. What that means is that there is a cohomology theory whose zero space is the infinite cohomology, is the even cohomology of this space. And this is compatible with the sort of product structure in this thing is compatible with Whitney's sum. So the product structure in this cohomology, the addition, if you like, is the multiplicative group of units. All right, so this was an old question that was asked by Graham Siegel years and years ago, and a lot of people had tried various things, various direct algebra topological constructions to give this infinite loop space structure on the product of Eilenberg-MacLane spaces, and it never worked, but somehow algebraic geometry just miraculously does it. Okay, so now let's come to real and quaternionic algebraic cycles. So let's go back. Again, we have complex projective space with its real structure given by complex conjugation. And I remind you, the fixed point set is just the real projective space. And now this action not only extends to the symmetric product, as we saw before, but it extends to algebraic cycles. So it gives you a Z2 action on the space of cycles whose fixed point set corresponds precisely to the real algebraic cycles. Now, the real algebraic cycles may have no real points. This is always this little. But certainly among these are the real algebraic cycles that consist of honest real points. at any rate, let's look at this group. It's a topological subgroup of this group, and one can naturally ask, what is its structure? Okay, so we thought about this years ago, and the first thing that we showed, this was Paolo and Marie-Louise and I, we showed that there was an algebraic suspension theorem of the kind I mentioned before, but which is equivariant with respect to this complex conjugation. In fact, there's a very general one for finite group actions, which is a kind of delicate matter. But in the case of this complex conjugation, it's not that hard. And so this means that, in fact, there's a kind of real suspension of the real cycles, which gives us homotopy equivalences and allows us to desuspend down to 0. And then you compute, and you can actually say what the homotopy type of this space is. Well, before I give you the whole homotopy type, I should mention that there's a piece of it which is interesting. Namely, you can look at the real cycles and divide out by the ones that are kind of trivial. I mean, if you're given any cycle, you can just take its image under the involution, add them up, and the sum is trivially invariant. But we're not interested so much in those as the ones which are actually already invariant. And so we divide by the average cycles, and we get a group which is it's a topological group, but it's actually a Z2 vector space on the irreducible real varieties. And it turns out, this is a theorem of a graduate student of mine, that there's a homotopy equivalence of this space with the product of Eilenberg-MacLane spaces now in every dimension between 0 and Q, but for the group Z mod 2. And so, again, everything I mentioned before goes through. The real Grassmannian maps into here, and that classifies the total Stiefel-Whitney class. The algebraic join makes sense, and it classifies the cup product, and there is an infinite loop space structure. So the whole package sort of carries over to this case. But this is for this reduced space, and if you don't divide by that, the question is, what does it look like? And so here's the answer. Main point of the answer is that it's complicated. So if you look at the real cycles of codimension Q in projective space, they're a product of Eilenberg-MacLane spaces. That you expect from a general result. But what are they? Well, they start off simply, but as time goes on, they get more and more complicated. And this is so you can see if you fix this dimension, there are a number of them that you get. And the best way to understand what this says is to look at the picture. So this is the picture, and that you see you get Z's up along the diagonal. They're going to more or less correspond to Pontryagin classes. And then you get Z2s along here. That's what we just saw from the theorem of Lamb. And then you get all these other classes. If you want to know what happens in any given dimension, you have to look at the diagonal. So on certain diagonals, you just get Z2s. In this diagonal, you get a Z plus 2 Z2s. The next diagonal, you get just Z2s, 3 Z2s. Okay, so that's what it looks like. We wondered about this. And at a certain point, we figured out that if you look at the homotopy groups, it's actually a lot simpler, but that's a story I won't go into. But the real question or the real answer to everything came when we started asking a more interesting question, namely, this space is a Z2 space in the sense of topology. It's a topological space with an action of the finite group Z mod 2. And so it's a natural question to ask, what is its Z2 homotopy type? What does that mean? Well, you sort of plunge into the world of Z2 spaces, it's spaces with Z2 actions, for any finite group G, G spaces, and then G maps between them, maps which commute with the action. And once you have G maps, you can talk about G homotopies, and therefore G homotopy equivalences, and so forth and so on. Just everything is in this category. And so in particular, G equivariant homotopy type just means that there's a homotopy, it's the equivalence class under G homotopy equivalences. Well, this leads you to equivariant homotopy theory, a subject which you need to be introduced to by a friendly person, because if you look at the literature, it abounds in these big tomes, every inch of which is unreadable by mortals like me. But the general concept is that, as I say, you plunge into this world of G spaces and G maps. And one of the important points of the theory is that the invariants that you get are no longer indexed by the integers, as in usual theories, where homotopy groups and homology groups are indexed by the integers. But they turn out to be indexed by the real representations of the group G. And let me give you an example. In ordinary homotopy groups, you're just mapping the sphere into X. Okay, but now we've got a finite group G lying around. And so the natural thing to do is to take the sphere, which is the one-point compactification of any finite dimensional representation of this group G, and look at the equivariant maps of that sphere into X. This is a very natural thing to do. And in fact, this is really what comes up if you think of doing Morse theory. I think the best way to sort of understand why you would want to do this is, take a manifold with a finite group action and a function which is invariant under the group, and look at what kind of cell decomposition you get. And you're kind of led to thinking about these things. But let's just take this at the moment. So for G space, the homotopy groups are indexed by the representations of the space. Now, it turns out that given that, you might say, so it turns out also that the homology and cohomology groups are quite analogously indexed by the representations, and they can be, the whole mechanism attached to a space is quite complicated. But there are Eilenberg-MacLane spaces with homotopy characterizations for every finite dimensional representation and every Mackey functor Z and the Mackey functor Z, or any other Mackey functor for that matter. You can take quite general coefficients that transform in funny ways under the group. There is an Eilenberg-MacLane space associated, uniquely characterized by certain homotopy groups, and which classifies this functor, okay, by G maps. Now, interestingly, although all this was lying around, no one had ever thought to prove the Dold-Tolm theorem. So Paolo, who began to learn this, proved this beautiful Dold-Tolm theorem. Namely, if you take this sphere I'm talking about, take a finite dimensional real representation of a group G, take its one-point compactification, that's the sphere SV, and look at the free abelian group on it, that's a G space. That is the Eilenberg-MacLane space indexed at V with coefficients in the simplest, within the integers. Let's just think of it as in the integers. Okay? And then, sort of building on this, I had a graduate student, Pedro. These guys know, infinite amounts about this theory. I know just about enough to be able to put up a couple slides. But they proved this incredible theorem that the codimension Q cycles on projective space under the involution are again a product of Eilenberg-MacLane spaces. But here you have to look at not at the usual Eilenberg-MacLane spaces. They're Eilenberg-MacLane spaces indexed at the representation of the group Z2, which consists of k times the trivial representation and k times the sign representation. So that's nothing but the complex numbers with complex conjugation, CK with complex conjugation. That's a certain representation. You see it in a T is K theory, where he calls this the sphere SKK. Right? So you've got this map on it. Now, this is really gorgeous theorem. In fact, Pedro proved again that the whole package goes through. He computed the equivariant Z2 cohomology of the Grassmannian, showed that it's over this Mackey functor. It has a canonical generators C1 through CQ, and the natural inclusion as a Z2 map classifies the total Chern class in exactly the same way that I said before, 1 plus C1 plus C2. Okay, and this just comes from the usual cell decomposition of the Grassmannian, so it is natural. So I'm going to take just 2 minutes. So what happens in the Quaternion case? And this is when it got really interesting. So suppose you go back and look at projective space with the Quaternion involution. Okay, so now this is this fixed point free involution. Nevertheless, although it fixes no points, it does act on cycles, and there are a lot of fixed cycles. There are lots and lots of interesting cycles which are invariant. Fermat cycles, for example, which are really invariant under the Quaternion involution. In fact, they form the Quaternion subvarieties, cycles form a nice subgroup of this with a very interesting topology. So you can ask, what does it look like, just as I did in the real case, and there's a quaternionic suspension theorem that we proved when we proved the real one. But when you do the quaternion suspension, you have to suspend to a new quaternion space. So the codimension goes, or the dimension goes up by 2. The dimension goes up by 2. And so when you stabilize, there's sort of an even stabilization and an odd stabilization, as we saw back with the symmetric products. They come in 2 flavors, even codimension and odd codimension. Nevertheless, we figured out exactly what it was, and so again, there was a complicated picture like the one I showed you before. And Pedro and Paulo actually figured out what the Z2 equivariant homotopy type of this thing is. And the Z2 equivariant homotopy type is this strange structure. So the odd cycles as a Z2 space on this Brouwer-Severi variety, when stabilized, look like maps from the Brouwer-Severi curve, the plus means with the disjoint base point. So continuous maps from the Brouwer-Severi variety into this space. And the even ones are the same, except you're mapping into the Eilenberg-MacLane space indexed over the even integers. Here it's over the odd integers. So again, it's beautiful. I mean, if you try to compute, invariance in these spaces, they're enormously complicated. So this may already be more than you want before lunch, but let me tell you, it's a huge simplification. And what this means is that what's being classified, homotopy classes of maps of X into Z odd, simply classifies the equivariant cohomology over the odd indices indexed at the KK representation. Okay, not of the space, but of the space crossed with the Brouwer-Severi curve. And the same thing in the even case. So let me indicate why that might be natural. And then I'll be done. There's something called KR theory, which is an extension of a KH theory, which extends T as KR theory. You start with a space with an involution, and Atiyah defined a K theory by saying that you look at vector bundles over this space, which are complex bundles with the property that there's an antilinear map covering the involution whose square is 1. Okay? And that forms a very pretty theory. It plays a huge role in the index theorem. And now you can think about a quaternionic analog, namely you have an involution on the space, and you take vector bundles over it that are covered by an antilinear map whose square is -1. Whose square is -1. And then you make up the sort of free abelian group generated by isomorphism classes of these guys. And this forms a K theory called KH theory. But this theory doesn't have a tensor product, because the tensor product of 2 quaternion bundles is a real bundle. In order to make it into a ring, you have to take the direct sum of the real bundles with the quaternionic bundles. And then it has a ring structure. And it turns out that the KR theory of the Brouwer-Severi curve crossed with X is indeed real K theory, direct sum with quaternion K theory. In other words, this is really a ring now. And so this... I want to say anything else? Yeah, so I'd just say that these guys actually prove the whole package in this case. They showed that the cohomology of the quaternionic Grassmannian, when stabilized, is generated has specific generators, and this map classifies a new total equivariant Chern class. Nobody ever knew about this before, and everything actually extends to the algebraic category, so they have a really nice sort of theory of varieties. And it's all related to an old computation of the algebraic K theory of Brouwer-Severi curves over an arbitrary variety X that Quillen did years ago in his bombshell paper in algebraic K theory. So that's all I have to say. Thanks.